Hi, thanks for the introduction. Again, I am Darren Guinness, and I'm presenting the Haptic Video Player using mobile robots to create tangible video annotations. And this was done with the help of my collaborators, Annika Muehlbradt, Szafir, and Shaun Kane at the University of Colorado Boulder. So the overview or quick idea here, in this work we kind of set out to answer the question, how can we use off-the-shelf robots as an assistive technology in representing spatial content and relationships to individuals with vision impairments. And just to kind of better understand and contextualize why spatial relationships are important in science and in other types of educational areas, consider an image of the solar system. So for this image, we can really think about making this diagram accessible in a lot of different ways. And there's a whole bunch of different features which you can consider representing to somebody with vision impairments. So features that we might want to convey in detail might be something like planetary mass, planetary scale, orbital distance, orbital periods, and other types of relationships which change over time or involve motion or speed. So there's really a lot going on in this diagram, and that creates a problem using traditional assistive technologies. So the first approach we might take is to use a tactile graphic or a tactile diagram. What this really means is that it's a representation that can be explored through touch. So a blind person can kind of gain access to a structure or layout by feeling around a 3D printed or raised line representation of a diagram. And this is really great to convey static spatial relationships and structure. But there's a couple problems here, mainly that tactile information requires a lot more space and cannot overlap with each other. And it's easy to overload a user with too much information in a graphic. So when considering tactile methods for non-visual access, we mainly want to use tactile graphics to represent constant relationships between objects or representing spatial layouts such as in maps and other types of simple diagrams. We may want to consider other methods when considering things that change or co-occur over time. Emphasis on movements and speed and kind of trajectories. These types of things are hard to represent in static tactile forms, especially temporally. So we may want to consider using other methods in this situation, and when there's a large amount of information to be displayed. So another way that we can think about enabling access to different types of dynamic or video content might be actually to use audio descriptions. And really what audio descriptions are spoken descriptions of background information that are not presented in captioning. Important contextual bits that are present in dynamic presentations but may not necessarily be read by a screen reader or disclosed via open or closed captions. So here we might consider describing the motion of this satellite Cassini, or the spacecraft Cassini, and its descent into Saturn.
Cassini streaks across a gray-blue sky, Saturn's white grooved rings behind it, the world buff-colored curve of Saturn beneath.
So we can start to get an idea of what's happening that may not necessarily be presented in a non-visual format through audio descriptions. Another method that we can make dynamic content accessible and spatial content accessible is through encoding information via sound. This is known as Sonification, and really what it means is that we can kind of map different types of information to pitch or tempo or tone in order to convey different relationships and kind of compare two different objects. So here we can actually see a diagram which represents the Earth's orbital period as well as the Mars orbital period, and we can start to actually listen to this difference through sonification. So I'm just going to play two here. This is Earth's. It's kind of soft. And so the tone here is actually being mapped to the mass. And it's an inverse mapping, which means that larger objects are going to produce a lower tone. And higher pitched objects are going to, smaller objects are going to produce a higher pitched tone. But we're also actually gaining access to the orbital period here, which is something that's changing over time. You'll notice that this audio is circular, which is representing basically the orbit and its duration. The tone, the actual tempo of the tone is representing the movement speed as well. So it's important to consider when to use auditory methods for non-visual access. Audio descriptions may be great for representing information in the background and providing high-level summaries of things that are going on. And sonification may be used when the user needs to compare the relationship between objects or get basically a rough estimate of some difference between two different stimuli. So we may want to consider other different types of assistive technologies when the user needs to precisely compare movements or spatial structure. And also we know that audio can interfere with other competing instructions, such as when you're in a classroom. It can be very harmful for you in order to try and keep up with the classroom lecture while listening to your assistive device, which is kind of conveying things to you. So here we see a new opportunity for using robotic displays to present spatial information non-visually. These types of displays offer advantages for representing precise spatial information through touch. And we can start to represent things like form, scale, movements, and even more. The only problem here is that these are very expensive to produce and are not available to the consumer. So here we see the Inform project from Shaun at MIT. And we want, out of this we see a large potential opportunity to create a set of tools using off-the-shelf robots to make spatial concepts and relationships accessible to individuals with vision impairments. And that leads us to our system, the Haptic Video Player, which allows a person with vision impairments to gain access to motion directly over top of video content using robots, small wireless robots. And basically, the individual can hold or touch a robot and kind of track its movement as it moves across the display, offering a multimodal representation of what's happening. And an emphasis and a priority for us during this entire project is to use off-the-shelf hardware. Really what this means for people with vision impairments is that they can immediately start using these types of setups and systems using just consumer-grade materials, which doesn't necessarily need you have to learn how to program a robot or learn how to construct a robot. And for this work, we used a touchscreen tablet. This is the Microsoft Surface. And the Ozobot Bit, which is a $50 cylindrical robot, spherical robot with two wheels on its undercarriage. So in order to convey content in video, we quickly realized that not all video content needed to be represented spatially. Things like talking head, interviews, other types of situations in which you may not necessarily need spatial access, which is why we came up with this idea of the haptic annotation. In a haptic annotation, spatial events are conveyed over top of existing video and can convey things like movement, speed, and layout or structure. And basically, a video can contain one or more haptic annotations in order to be considered a haptic video. And so whenever a haptic annotation presents itself or begins, it has a life cycle. And so there's a set of states associated with this annotation. And the states would be idle, introduction, tangible reflection, and a completion of the annotation. And basically what a haptic annotation does is the robots kind of move and act out each state in the life cycle and kind of wait on the side of the display when they're not being active. So basically the robots wait on the side of the screen until a haptic annotation begins, in which they move out to their positions. One thing that's represented here that's not represented here is that the user is actually presented with a auditory overview of the scene, presenting basically contextual bits of information, such as the fact that the robots are reflecting a satellite which is moving in front of the sun, and the relative brightness level observed by basically a scientist in a lab. And in step 2, this is tangible reflection. This is actually where a person with vision impairments gets to start to understand what's happening via touch. Here we see a robot reflecting the sine and cosine waves. And you can kind of feel and kind of touch the robots to feel and understand what's happening. As an annotation finishes, we need to put the robots back to their home locations. Basically, the robots need to move back and wait until the next annotation. And so the robots kind of move off of their path, and there's a small loading sequence that's announced to the user so that a person with vision impairments knows that this is not necessarily important to the context of what you're studying. And so we also realized quickly that we needed to create ways to represent and create haptic annotations. So we created this gesture-based authoring tool, which allows you to just basically using small strokes and a small mouse wheel, iterate through scenes and kind of scrub through and add trajectories as the video kind of, as the objects move in the video. So it's actually up to the user to manually craft this, but we have explored a little bit of methods in terms of automating this process. So we also, in order to understand if people with vision impairments could even use this to infer structure and kind of motion that's happening in video content, we performed a user study with 7 individuals with vision impairments. And these vision impairments ranged from just above legally blind to basically complete blindness. The goal here was to see if people with vision impairments could use the player to follow along with video content via robot motion. And we employed a think aloud procedure and kind of asked participants to characterize what was happening through basically spoken voice. So in the first task, we asked users to locate a single robot on the display. This robot moved, so we actually asked them to basically tell us where it started and finished. In the second task, the robot basically drove in a circular pattern, and we asked users to kind of characterize what was happening. In the third task, we saw participants locate 2 robots, which had unique motion to them. And in the fourth task, we asked a user to identify the direction of a robot's motion. Finally, we asked the users to characterize differences in robotic speed being represented. So overall, we found that participants had some varying levels of accuracy to this, but they were able to recover the actual motion being conveyed through the robot motion. So the actual motion on screen being conveyed. We kind of created a rubric, and kind of a grading rubric, and basically compared the participants' answer to this rubric in order to come up with this accuracy diagram. So we saw that participants made a couple errors during their characterizations of the motion. Mainly, we saw that in location tasks, participants underestimated the robot's final location with respect to a quadrant or corner of the screen. We also found that in shape recognition tasks, participants characterized the circle as an oval or a spiral. Some of this was due to the fact that if you held the robot and you kind of started to adjust it off path, the robot would actually compensate via its motors, and it would create a wave-like texture as you held onto it. We also saw that in tasks with 2 robots, participants misidentified a robot. These robots were labeled, and so we were asking them to basically to characterize each robot and its trajectory. And participants identified the wrong robot according to basically map the wrong robot and swap the names. We also found that users liked using this system, found it to be easy to use, but in terms of informative nature, we kind of still need to increase a little bit of precision here. So just to sum up, our key findings is that people with vision impairments can interpret visual motion via the output of robots, and off-the-shelf robots can introduce some trade-offs, size versus power and cost versus control. Participants also found a whole bunch of ideas and things that they wanted to use this type of setup for, including map content, blackboard lecture videos, handwritten lessons, and knot tying. So just to conclude, off-the-shelf robots can be used to convey spatial concepts to people with vision impairments so that they can follow along in videos. And there's increasing opportunity in using inexpensive robotic-grade materials which are off-the-shelf in accessible spatial information presentation. Thank you.
Thank you, Darren. Any questions for our speaker? I had a quick question. It was kind of hard for me to see from the video, but is it possible for the participant to actually move the robot off its path?
It is.
And what happens?
That did happen a couple times.
What happens in that scenario?
Well, we actually found that participants oftentimes were able to navigate the robot back. If you just kind of move the robot around, as long as it discovers the line, it will basically recorrect itself. However, this is a problem that we are seeking to accommodate and are doing that right now. Thank you.
All right. Thank you so much. Big hand for our speaker.